So tell us about while we're waiting for this to load.
Okay, the original I modified was just this thing that draws like this sort of circle pattern type thing. Oh, there we go. From a bunch of purple lines, and it draws lines out from the center and then rotates them around.
Oh, yeah, cool.
And then spirals out.
So the lines get longer each time and rotate slightly by the looks of it. Yep.
I modified it actually pretty significantly. Well, it looks different, but.
Let's circle mode. Alright, so you've. Oh wow.
So yeah, I basically changed quite a lot about it, like the stroke weight of the line, and I added a mouse click so you can reset it. And it basically, as it rotates out, it's incrementing this R variable, which is determining the rotation of the lines, and that's also being used to find a value between 0 and 225 for the green and blue settings.
Cool. That's really cool. That's nice. Well done. Easy.
Yeah, it's basically Java, so I've used that before.
Okay, cool. No, that's good to hear. All right. All right, talk us through.
Yeah, it was basically a mesh wherein in every vertex, you can put a sphere, and as you move the mouse, it zooms in on.
Right, so the.
Yeah, and I didn't change I just changed the spheres. I mean, there were rectangles before, I just changed the spheres and background and some color values and stuff.
Cool. So you can see how slow this computer is. I can't even render that many spheres, but that's all right. That's cool. How'd you find working with processing?
Yeah, pretty. I had to work more.
Yeah?
Yeah,
Okay, no, that's cool. As I said, it's just to give you guys a chance to have a little play around. And just in time. So what was your one called? Spiderweb. This was your one, wasn't it?
Yeah, that's one.
All right, so talk us through.
So basically, the original one used lines to do like painting.
Mm-hmm.
So for me, I'm doing circles, and as it goes on, the circles get smaller and more defined.
All right.
So you just have to wait for a while. You can recognize the picture.
Something's happening. Oh, is it the Google Cricket logo, is it, or? Oh, yeah. I don't watch a lot of cricket, so I'm most familiar with the Google Doodle the other day, so my apologies. Although the India-Australia game is today, is it?
Yeah, today.
And everyone's rooting for India, are they? Or?
I don't know. The news this morning, they think India is going to be a better, easier opponent in the final.
Yeah,
but they want an Australia-New Zealand final because they.
Yeah,
that be some sort of payback for the Trevor Chappell underarm ball.
Yeah, I was actually talking to a German friend of mine last night about the the New Zealand-South Africa semi-final, and being German, she had no idea. And the conversation actually ended with the underarm ball. So, it's sort of the combination. For those of you who don't watch cricket, search Australia, New Zealand underarm bowl, and you'll see why everyone, 20-something years later, is still talking about it. Right, anyway, so cool. Thanks for the people who did that. For the rest of you, try and, if you get a chance, do it.
I've done the examples in the programming interactivity book.
Yeah. So, actually that brings me to another point. I'll have to figure out what Mark wants to do with the programming interact. Have you guys got copies of the book? Or?
I have two. I'm borrowing, I think, from last year's master's students.
Okay, why do you have two?
Charles's one, and I don't know.
Okay, yeah, I'll talk to Mark anyway, because that's sort of what a lot of the material is sort of based around that thing. So I'll talk to Mark and see what his thoughts were. But he didn't give you guys the book at the start. No, okay, sweet. Yeah, so I don't know what his thoughts are. Anyway, so we'll continue on with Tuesday's lecture. So we had a little bit less left to cover here, and then a whole lot more to cover in this, what's supposed to be today's things, but we probably won't get through them either, but that's all right, we'll do our best. All right, so if you remember, we had a bit of a sort of refresher on programming. We looked at a bunch of different things, all the basics of programming, then we looked at a little bit of object-oriented programming with the idea of classes and objects. So I sort of whipped up that simple car racing demo, which just had two cars which move along the screen. Talked about things like, how we can construct multiple objects and different constructors and stuff like that. Anyway, so we talked earlier about how processing is sort of a language of interaction and stuff like that. So we've covered sort of the basics of programming, and now at least some of you have had some experience having to play with processing, so hopefully some of that sort of gelled. So let's actually talk about some of the interaction in processing. So why did I close that? That was really dumb. I have to wait 10 minutes for it to open again. Process. Yeah, so processing is a language of interaction, so it basically makes interaction really easy, and we're going to have a look at a few different ways of doing it. So let's just start up with our default settings, background. Hopefully this is looking familiar to everyone now. Right, so, size 255, background white, nothing new there. So let's say we want to do some mouse interaction. Processing has a couple of built-in, or quite a few sort of built-in things for handling interactions. So for example, we have mouse X, mouse Y, which will basically tell us the mouse X, mouse Y position on the screen. So you'll see as I move over the top left corner, we're getting closer and closer to 0 by 0. As we move across, the mouse X value gets larger and larger until we get to 512. And as we go down, the mouse Y value gets larger and larger until we get to 512, if I can get the mouse close enough. So yeah, 0, 0 is in the top corner, and then it goes 0 to width across this way and 0 to height down this way. So that's all nice and simple. So we can do some, if we wanted to, we could do some really basic graphics. A really simple sort of example where we draw circles wherever the mouse is, easy peasy. Or we could do something slightly more interesting. Oops. And now the circles will get larger as we move to the left-hand side of the screen, the right-hand side of the window. So pretty easy, cool. What else have we got? Let's say we want to do a simple drawing program. What we can do is we have two variables in processing which are automatically set up for us, mouse pressed and mouse button. So let's have a look, see what they do. So you see at the moment it says false and 0, so mouse press is false and mouse button is set to 0 when I'm not doing anything. If I click the left mouse button and hold it down, it says true and 37. As soon as I release it, it's false. So mouse press is obviously true if I'm holding a button down and false if I'm not. And that's right mouse button is 39. So left mouse button is 37, right mouse button is 39. And if I do both, which is the equivalent of a middle click, it's 3. So you don't actually need to know those values because I'm pretty sure from memory. Oh, actually, I should pop this open just to double check. Pull open the processing website, but I'm pretty sure mouse button equals, whoops, left. So there's a few sort of macros which have been set up for us. So we have left in all caps is basically the left mouse button, so that will store the value 37 in it, and then there's also right, and I believe, no, maybe not middle. Let's have a look. Mouse button, again, all the documentation is in here already. Left, right. Okay, so perhaps there's not one center. Thank you, good spotting. There we go. So we can now do some pretty simple interactions. Let's say if mouse pressed, so if I'm holding down a button, let's draw, and if mouse button equals left, let's draw an ellipse. Else if mouse button equals right, let's draw a rectangle. And this time we'll make it scale it based on the Y position of the mouse. And else, so if we press the middle button, let's just clear the screen. And we need one more close. So now if I press the left mouse button, I can draw circles. If I push the right mouse button, I can draw rectangles. And if I push the middle mouse button, clears. Easy. So there is actually two ways of doing this in processing, and a lot of the functionality, particularly interactive functionality in processing, has multiple ways of working with it. So we've got these variables which processing automatically sets up for us: mouse press, mouse button, mouse X, mouse Y, and so on and so forth. But there is also function prototypes that we can overload, or override. So, you know, we've got setup and draw, and what else? There was one other one we looked at. I can't even remember off the top of my head what it was. Was it mouse? No, we hadn't looked. There was something we looked at on Tuesday anyway. We're going to look at mouse move now. But yeah, as Robert said, mouse moved is a default function, and that will tell us if the mouse has moved. We also have mouse dragged, which is the same as mouse moved, except only fires if the button's down, and mouse released, which will only fire if I have let go of the button. So now if I move the mouse around and I'm not pushing any buttons, we get mouse moved. If I'm holding a button down, I'll get mouse drag, and if I release it, I'll get a single mouse released function. So we can actually basically redo all our functionality in here just by using these functions rather than putting it in the draw function. There is no right or wrong way to do this. It's just whatever works better for you. If you're the sort of person who wants to have everything in the draw function or like called from the draw function, you know, processing allows you to do that. If you're more of an events-driven person and you'd rather like just have functions which get called when certain things happen, processing works for you as well. So, you know, there's no better way or worse way of doing that. It just depends on what you're trying to do and what you're most comfortable with. And as I mentioned, processing sort of does this for a lot of different things. A lot of different interaction things will have multiple ways of doing that. We're going to look at a few more as well. So keyboard interaction, we've looked at how we can interact with the keyboard. Let's open a new sketch. Let's do the same thing with, we've looked at mouse. Let's look at keyboard now. So we can do stuff in our draw function again. If, what is it, key pressed. So we have the key pressed function, which will fire if we press a key. And we have this pre-set up variable called key, which will tell us what key has been pressed. So my draw function, let's just move this over here. So key pressed, Q, E, W, R, T, so on and so forth. So you'll see like that fires multiple times because the draw method's running over and over and over again. So as long as the key's being held down, essentially it'll do it. So this is a case actually probably where there is a slight difference. If you only want to register that the key's been pressed once, you might be better off calling the key pressed method. So we have, again, another method, key pressed. Println, KP, key. And let's just comment that out. So now if I press it, it's only going to fire once, or if I hold the button down, it will fire at the repeat rate of the Windows is set up to. So if you want something which is only going to happen once when you push the key, you might want to look at key pressed. Otherwise, if you just want to detect when the key's been pressed any time or when the key's been pushed down, draw method will do it. Obviously, there's ways you can make both work in either way. So we could have in here, I think there's also avoid key released. So there's a key release method which will let us know when a key's been pressed. So if we wanted to recreate it, we could have key down equals false, key down equals true. And that will basically, by what we're doing is when we press the key, we set a boolean to say the key's been pressed, and then when we release it, we say, okay, the key's been released, and in here we could have key down. And this should theoretically basically act exactly the same way. Oops, if I use the right, so it's boolean in processing. So now we're using the key pressed and key released functions, but it's basically functioning the same way as the draw function is. So you can, even though they work slightly differently, you can make it work either way. And again, it just comes down to your personal preference, what you're trying to achieve and things like that. Everyone follow along? Yep, cool. Yeah, so, for the mouse and keyboard interaction, it doesn't actually make a huge amount of difference which one of these you want to do. You can always make it work one way or the other. Just depends on, what you prefer doing. Okay. So obviously using all the default sort of drawing functions in here, we could draw our own windows. So we could draw a box and then put some other boxes in it. If you look at, even the windows, which are, a little bit more complicated. You can imagine you can break this down into individual elements and stuff. You can draw it, but that's going to take a long time, and there's going to be a whole lot of messing around to achieve not much. Fortunately, a whole bunch of people have put together various windowing solutions, or GUI solutions rather, for processing. So we're going to have a look at one main one anyway, called Control P5. So Control P5 has been put together to basically allow you to do a whole bunch of different GUI elements. So this is an example of the sort of things they have. So they have drop-down list boxes, they have multi-level lists. So, snap. Okay, so they have drop-down list boxes, so you click on that and it pops up, and then you can scroll down and choose your one. They have multi-level lists, so you can, you choose level 2, and then level 2 pops out with a whole bunch of things. Radio buttons, so radio buttons are ones where you can only select one option. A range, so we can set the bottom and top. Sliders, so vertical sliders, you can move up and down. Text fields, you can enter text. Number boxes, which are text fields but they only allow numbers in them. Check boxes, so they're kind of like radio buttons, but you can select multiple ones. Regular buttons, which can be toggle, so you push them on, they stay on, you push them off, they stay off, or you just push and they're on while you hold the button down. Knobs, which you can twist, sliders. So yeah, this is just a selection of some of the things. There's a whole bunch more. And it's got support for open sound control. So we're going to look at this later, probably more when we're getting into the hardware side of things actually. The Open Sound Control was a set of networking libraries which were built a long, long time ago for communicating with MIDI instruments. So MIDI, just as a bit of background, is sort of like I don't even know the best way to describe it because I haven't worked a lot with MIDI, but it's basically a way of representing music in a data format that's interchangeable across various instruments. So you can say, play these notes using this instrument, but then you can change it for a different sort of instrument and it still knows how to play those notes and so on and so forth. And the reason they had these things is so people could use synthesizers and stuff like that, and then that you could store that data on another machine, or you could send it to you could use just a little synthesizer and send it to a computer to process it, so on and so forth. Open Sound Control was developed basically as a way to send, I'm pretty sure anyway, that originally it was designed around MIDI, so you could send this data over a network. The people who designed it actually did a really nice job. It's a very human readable networking thing, which does mean that it's perhaps not as fast as possible. For MIDI music, it's probably not that important because, if you're writing a song and it takes, a little bit longer to send that data, it's not as urgent as if you're streaming video or whatever, but yeah, it's sort of taken off. It's been supported by everything. So if you find a microcontroller, someone's guaranteed to have written an open sound control for it. If you're using a programming language, you're guaranteed someone's going to have written, unless you've written the programming language yourself, you're almost guaranteed someone's written an open sound control wrapper for it. So it's, yeah, a really nice way of sort of interacting and data communication between various devices, various programs, and so on and so forth. We're not going to look at it now, but it's nice to know because basically you can use Control P5 and you could use that to, say, control an Arduino. So you could make a nice little GUI using processing, plug in your Arduino, and then communicate with the Arduino using open sound control. And we'll look at the format later, but basically all you do is say, here is the thing I'm affecting, and here's the value. So you'd say, button 1's value is on, label 1's value is hello world, blah, 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 blah. Yeah, we'll look at it in a lot more detail later on, but just to know. So yeah, of course, Control P5 comes with a fairly exhaustive reference thing. It's not quite as prettily set out as the processing one. This has been generated using Google Docs, which is an automatic sort of documentation generating thing, but you know, it works, but it's not particularly pretty. But you can see these are all the various sort of classes and packages which are available to you. You can open up one, so let's say the color picker class, and then it has a little bit of information. It's got some examples. It's got methods, all sorts of bits and pieces. The methods all have descriptions. So there's still lots of information in there. It's just not perhaps as nicely set out. So I've already had a look at that. So let's have a look at how we can use Control P5. File, new. So first thing we're going to want to do is import the library. So you're going to go into your add library and you're going to go to Control P5 and you'll see it's in there, and you hit install, it'll download it and install it. I already did this. The one thing I was organized enough to do. But once that's done, you'll see it pops up in here, and you can hit import Control P5, and there we go, import Control P5, we're done. So the way Control P5 works is we have this Control P5 object, which we need to set up initially, like that. And that's going to be responsible for building all our GUI. So we need to create that. And then in our setup function, we're just going to go call new Control P5, this. So basically every Control P5 project you're going to work on will have these, 5 lines of code in it, or I suppose if you don't count setup, these 3 lines of code in it, which is specific to it. So we need to import the library, so we need to tell processing I'm using Control P5, here's where you find it. We need to create a Control P5 object, because that's what we're going to use to create all our GUI things. We're going to basically say Control P5, create me a button or whatever else. And then in this line, we're going to initialize it. So if you remember from Tuesday, this is how we create classes. We say new, and then the name of the class, and we pass in an argument. So in this case, we're passing in an argument called this. This is, I'm not going to go into too much detail, but this is basically a special word in Java which represents the currently running process or currently running program or currently running class. But basically it's saying, the way Control P5 works is it has a bunch of what's known as callback functions. So if you click on a button, it will run a function. So like just how we saw before, how we have a whole bunch of functions which Java or processing gives us, like mouse move. Control P5 will give us functions like void, where is this one in here? Void button 1, for example, if we create something called button 1. So by saying this, it knows I can create, or I can call a function called button 1 in this class, and it will do something. But yeah, so anyway, let's have it start. So if we create this, nothing, no surprises there. All we've done is set some stuff up. We haven't actually told it to do anything yet. So let's just do some things. All right, so let's, overshot by 2. So, okay, we've got our Control P5 object. Let's actually do something. So let's create a new button. Button 1 equals cp5.add button 1. And let's do a color picker. All right, so, the syntax for this is pretty straightforward. So there's a whole bunch of different objects which control Control P5 allows us to have, and we can have a look at them in here. So accordion, button, canvas, blah, 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 blah. There's a whole ton of them we can put in. So obviously a button is a button that you click on. Color picker allows you to choose a color and so forth. And then what we do to add them to our GUI is we just call cp5.addButton, and we have to give all of our objects a unique name. So button1 is probably a terrible name, because then you're not going to know what that button does. But you probably want to give it a name based on something it's going to do. So on/off button or whatever else. But let's run our program now and see what we've got. So this is our control picker. So this is something I get stuck on every time, and I'm kind of glad that I got stuck on it so I can make a point. So you'll notice nothing is working. This is a little catcher. You need to have a draw function, even if it's empty, otherwise Control P5 won't actually let you do anything. Okay, so there we go. So this is our color picker object, so I can change the red value, and you'll notice as I change these values, that little color bar in the bottom will change colors to represent what's in there. So we have red, green, and blue, and alpha. So alpha is how transparent it is. So 255 means it's completely opaque, it's not at all see-through, and as I reduce that down, it becomes more and more see-through. You cannot really see it very well, but there is a button in behind there. If I click like that, you can sort of just see it flash. And the problem is that Control P5, if you don't tell it where to put things, it's just going to put everything in the same place. All right, so how do we change that? Well, every object in Control P5 has manipulators or functions that we can use to change its characteristics. So let's say, okay, let's move our button, and we have a set position function which allows us to move it, and we have a set size button which allows us to change its size. So all fairly intuitive, fairly easy to figure out. So now our button has been moved to 100 by 100, and its size is 200 by 100, so we can see it. So the way Control P5 works is actually kind of cool, and I'm just going to talk about this because when you look at the Control P5 examples, they all do this. But each of these functions, every time I call add button, it will return my button. If I call button1.setPosition, it will return my button. If I call button1.setSize, it will return my button. So every single one of these functions looks like this: button, set size, and then it'll do some stuff, and then it will return button like that. So you might be wondering, why is it doing that? Like, we're affecting the button, why does it return the button every single time? It's actually so we can do some quite cool things like this. So you look at this and you might think, holy crap, that's really confusing. But essentially what's happening is we're adding a button, and that will return our button. And then we tell our button, set position 100 by 100, so it'll update its position and return our button. And then we call set size 200 by 100, and so it'll change the size of our button, and it'll return that button, and then eventually that button gets stored here. So if we run this code now, you'll see it's effectively done exactly the same thing. So this is something that I've only really ever seen in Control P5 library, but it's actually quite powerful because it means rather than needing like line after line after line of code to do what we want to do, we can actually, when we create the button with a single line, we can basically set up all its parameters. We can say, put it here, change its size to this, change its color to this, change its text to this, so on and so forth, in one huge big long line. Whether or not this is useful or not, it depends on your definition of useful. But the reason I bring it up is if you look at the Control P5 examples, they're pretty much all set up like this. So they will be set up, add buttons, set position, set size, so on and so forth. Yeah, so let's just have, and actually I should have said this before, so once you import your Control P5 libraries, obviously if you go into examples, and this always takes a long time, you go into examples and then we look at contributed libraries, you see there's a Control P5 one in there now, and that has a ton of different things. And if we look down, here we go. So this is an example here, CP5 add group. So all they've done is they've just pushed enter. This is exactly the same as what we just looked at like that, but they've just put enter in it so it looks prettier. So adding a group, setting its background color, setting its background height, adding a bang, setting its position, setting its size, moving it to the group, so on and so forth. And if we run that, we have this nice pretty sort of example. So yeah, there's plenty of examples in there. Again, go through them, have a look. You know, if there's something you want to work with, if you want to know how a drop-down list, for example, works, open it up, run it, have a look, see, oh yeah, okay, that's how this drop-down list works. Item 29, whatever else, and then have a look in the thing and try and get a feel for how the code works and so on and so forth. So yeah, by showing you this, you know, the idea is just so you guys can understand why this works. Whoops. I don't know why that's just changed the color because it didn't change any of the code, but never mind. Right, so as far as getting events, so, you know, it's all well and good to draw some stuff on the screen, but, you know, if nothing actually does anything, it's kind of pointless. So let's have a look at how we receive events. So there is okay, so this is just getting more and more, there we go. So there is an event which control P5 provides us, which is called control event, and it returns a control event, or it takes a parameter called control event, and basically anything which happens with any single GUI element in control P5 will call this function. And what we can do is call, so there's this control event which has a bunch of parameters. So if we have a look, we can open our control event thing and have a look. So it has, we can get array value, we can get controller, we can get group, we can get ID, we can get name, get string value, blah, blah, blah. So a whole bunch of different things, but let's have a look at get name to begin with. So when I run this, if I click on this, my control event function gets called and it's telling me something has happened with button 1. And that button 1 it's getting is from here. You know, so I've called it button 1 up here and it's just said, you've named an object button 1, something's happened with button 1. If I change this one up here, you see it's now saying pick a 1. So this comes back to what I was saying before about how it's important to give your objects names which make sense, because ultimately that's what you're going to be dealing with. If you call everything button 1, button 2, button 3, every time you reference it in the code, you're going to have to reference it as button 1, button 2, button 3, and it's going to get pretty confusing pretty quickly. So don't use button 1, button 2, button 3. Give them proper names. Right, so as far as what we can do, so let's just copy and paste this code. It's going to take too long to write it all out. There we go. So a control event, we can basically check to see the name, see what's happened. So buttons can only ever be clicked. You know, that's all the button does. So we can pretty much assume that if the button has fired an event, it just means it's clicked, so we can print, oh, yep, button 1's been clicked. With our color picker, however, it has some additional information, so we can find out the red color, the blue color, the green color, the alpha color. So our control event C also has this method get array value, which allows us to check the array value. Now it's can be a little bit unintuitive because different controls will return or fill out different things. So if I called get array value on, if our button launched the event and I call get array value, the results in that will basically mean nothing. So it may change, it may not, but it doesn't actually mean anything because a button doesn't have array values, but a color picker does. So let's just have a look if we run this code, what's happening. So if I click this, we'll see control event button 1 was clicked. Picker value is 255, 255, 125.0.0.0, oh, it's 0.0001, 255. So, you know, these are integer values here, but they're being represented in get array value basically returns floating point values. So you can see some of these aren't 100% accurate. 125 gets 125.0001. 48 gets 48.0000, but close enough. You know, we can basically convert. We could just do our casting like we saw the other day, like that, and that will tell us what our actual values should be. So there we go, 255, 96, 255, 123, and so forth. So let's just have a look what happens if we do try and have a look at what's being stored. C.get array value 0. So if we call that on our button now, it's just said, I don't know what you're trying to do. Like buttons don't have array values, they're either clicked or they're not. So at best, it will give you some garbage. At worst, it'll say, well, in this case, it's array index out of bounds. So c.getArrayValue doesn't have anything. It's not initialized. So it's saying you can't get value 0 because there is nothing in the array. Yeah, so that's one way of getting the value of things as they change from Control P5. The other way is, as I showed before, Control P5 actually sets up for every object you create, it sets up a new method like this. So I could do this control event thing. Nope. Forgot to get rid of that. Or I could just use the method which is named after the object that I've created. So you can see they both fire, different orders, but you could easily use either of these. And let's just have a look at what is stored in value. One. So doesn't really mean much. The way Control P5 works is because we don't necessarily know what a function is going to do, every actually, what's it called? Pick a one. Every function we get will have an int value which is passed into it, even if it doesn't necessarily use it, like a button, or if, like the color picker, it has multiple values. So a color picker doesn't have one single value, it actually has 4. So there's other ways we can get out of that value. So if you have a look in here, we can call red value, green value, blue value, alpha value, and that the red, green, blue, and alpha values will be packaged up and stored in this integer value. So if we actually just print here, let's just put value like this, and have a look at what happens when we set our value. So pick a one value is negative 37,889. That doesn't mean anything to us because we're trying to, 4 values have essentially been represented in one single integer, but using this red, green, blue, alpha, we can break it out. So, it depends on which way you want to go. Obviously, doing it this way has some advantages. We don't have one, like if we have 100 GUI objects, we're not going to have a huge big control event thing if we basically use a different method for each thing. However, it's a little bit more tricky to get our data out sometimes. So for our color picker, for example, we have to break out the red, green, blue, and alpha values out of that. Whereas here we can just call get array value. So, it's a bit, well, it again comes down to preference. Both of them work in and do exactly the same thing in slightly different ways. This way is perhaps slightly better if you want to get something which has a lot of different values. This way is perhaps better for things with buttons which aren't going to have a value. Take your pick. Whatever works for you is the right answer. But yeah, just to sort of show, so we could easily go red value, green value, blue. And now we can use our color picker to change the color of our screen. So yeah, lots of various bits and pieces in there you can do with Control P5. Don't have time to go through them all, but I might I'll probably put something with Control P5 in the assignment anyway. So I'd highly recommend you guys have a look at Control P5. It may not necessarily be the greatest GUI thing in the world, but it works. It's in the officially supported, well, not officially supported, but the officially recommended list of plugins for processing. So you can just, install it from the processing IDE and stuff like that. And it provides a lot of functions. It works really well for certain things and so on. To mention, there are obviously other ones. So this is one called Interfacia. You are welcome to have a look at it. I'm not going to bother because it's a bit more tricky to get running, and I don't think it really has as many sort of widgets and stuff as Control P5 adds. It's also not in the list of recognized libraries. Brilliant. Import library. So if we search in here, for example, Interfacia is not in the list. So if you want to use Interfacia, you have to actually download it yourself and then pop it in the right folder and everything else. And I don't know that it's really being supported that much anymore, but you know, have a look. If you don't like, if you use Control P5 and think this is really quite awful, have a look, see what else is out there. And you know, in the assignment I'll probably say use something, Control P5, or if there's something else you prefer, use that instead. But yeah, just to let you know, there are other ones out there. So this is what Interfacia looks like. I don't even think it looks as nice as Control P5, but that's my personal opinion. So yeah. Okay, does anyone have any questions about the GUI stuff, Control P5, anything we've seen in processing so far? No? Cool. All right, so let's move into graphics, because ultimately everything you guys do is probably going to have some level of graphics. It's fairly likely that most if not all of your work will have some graphical element, be it just a GUI like we've just seen, or be it slightly higher. So let's have a look. So programming graphics, there is an absolute ton of stuff to know here. Some of you may have done graphics in computer science. So I know COSC offers, I guess, 200 level, or like Canterbury University offers 200 level. I think there's an HCI thing which has a little graphics element. Third year there is an entire graphics paper, and if you do honours or masters, there usually is. This year McCundon, who teaches it, is on sabbatical, so it's not actually. So if you wanted to do it this year, you're out of luck anyway. But so this is probably as in-depth graphics as you can get at the moment. While McCundon's away. But yeah, so there's entire courses can be taught on this stuff. We're going to try and bat through as much of it as we can in a single lecture. We will come back to it later on as well when we look at open frameworks, but let's get into it. So some of the things we're going to look at is transformations, creating motion and animation, bitmaps, pixels, and textures. So in processing, we have, obviously we can do 2D graphics by just drawing lines and other bits and pieces. Processing, there's actually another thing that we haven't looked at in the size function. So we've all seen size 512, 512, like that, and that sets us up with a default 2D rendering thing. There is also another argument that we haven't looked at before, which we can pass in, where we can say P3D, and that will set us up with the processing 3D thing. So now instead of doing 2D graphics, it'll set up everything assuming that you're going to do 3D graphics. What does that look like? Well, if I don't do anything, it's not going to look any different. And we can still do all our we can still do all our 2D rendering in our 3D canvas. Oh, helps if we actually put that in the draw method, not the setup. We can still do all our 2D rendering in the 3D thing. There it goes. And it's going to work just fine. But what this is actually doing is it's actually setting it up to say, okay, you should be expecting to get some 3D stuff in this. So yeah, be prepared for that. And I'd highly recommend having a look through, or having a look at this tutorial, because it goes into quite a lot of sort of detail about various bits and pieces, which we are going to cover some of, but this has potentially got a lot more sort of examples that you can step through and talk through stuff. So yeah, well worth having a look at. So yeah, P3D is built on top of OpenGL. So for those of you who don't know, OpenGL stands for the Open Graphics Library. It's been around for a long time. A consortium sort of put it together as a language which should be the same across multiple graphics cards and stuff like that. So, if you're a graphics card manufacturer, your NVIDIA, your is it ATI, NVIDIA's main competitor? think so. You know, and back in the old days, you had Voodoo as well. All these guys were basically sort of doing their own things, and if you wanted to write a program which worked on one of these things, you had to figure out how to communicate with that graphics card. Obviously, that sort of made it a whole lot more difficult writing software, because you needed to know, okay, I'm using this graphics card, it provides these features, you know, so I'm going to write this set of code. Then if you want to support someone else's graphics card, you have to do as well. So they're like, okay, well, this is stupid. You know, it's so much more work for developers. So they created a standard called OpenGL, which basically just says, okay, draw a set of points, and then it's up to the video card to say, okay, well, I've been told I need to draw these points, and let's do it this way. You know, since then, Microsoft brought out DirectX, which was sort of a competitor. DirectX and OpenGL are always sort of competing. The last article I read like a month ago said that DirectX is winning at the moment, but DirectX is Windows, whereas OpenGL is on Windows, Linux, Mac OS, PlayStation, Xbox. You know, it's a lot wider supported. So, you know, be it that perhaps it's sort of falling behind a wee bit, it's more ubiquitous, so it's probably more useful. But yeah, so anyway, quite a digression, but P3D is built on top of OpenGL. So it sort of has a slight OpenGL feel to it, but it's, again, because it's processing, it's tried to simplify things down. So when we render, we basically move the canvas or move out where we're drawing in the world by using things such as translate, scale, rotate, and we can save and restore the state of the canvas using push matrix and pop matrix. We're going to have a lot larger look at that in a minute, but here's the sort of thing. So this is actually just running in 2D obviously, but 2D is just 3D with no depth really. So here's an example which draws an arm, and if we have a look at the code for this, we can actually just copy and paste this, and in fact, pretty sure this demo is actually built into as one of the default demos in processing now. Let's throw this in here. So this one's only running on the 2D thing, but let's have a look. So we have a translate thing. So translate moves our things, moves where we're starting drawing. So if you think we start up at 0, 0, we basically say, rather than, okay, draw a cube or draw a box from 100 by 100 and make it 200 and 200 wide, we say translate by X by Y. So translate is essentially going, it's like when you're writing a Word document or whatever, you move the position of the cursor, and then when you start writing there. So it's the same sort of idea. We're going to say, okay, move by X in this direction, move by Y in this direction, and then rotate, we'll rotate everything. So if we were to draw a line this way, so we say draw a line like this, but then before we call that, we say rotate by 30 degrees. When we do that same thing, it's going to draw that line, but it's going to be rotated by 30 degrees. Then we have push matrix and pop matrix. So push matrix basically saves the position of, I don't know what you want to call it, the origin, the cursor, whatever. So it will save that state, and then when we call pop matrix, it will restore that state. So let's have a little look at this code. So this is actually kind of stupid because those don't do anything in this current setting. Right, so the way this works is essentially we have two lines which are drawn. So in our draw method, we call background, which clears the background. We calculate the first angle as being the position of the mouse X position, and we divide that by the width, subtract 0.5, multiply it by pi, which will basically convert it into radians, but it also means that the value of it will be between, well, this part here, we'll set the value of it between -5 to 5, because obviously mouse X is going to be a value from 1 or 0 to width. So if we divide that by the width of the screen, this will always return a value. If we're as far left as possible of 0, as far right as possible of 1. So basically dividing the mouse X position by the width will return a value between 0 to 1. We subtract 0.5 off that. So that's now going to be between -0.5 and 0.5. And then by multiplying that by -pi, essentially, so do you guys know the difference between degrees and radians? Well, actually, in this case, yeah. We're basically trying to convert from degrees to radians. So well, in this case, not quite. Let's comment out pi and see how that actually affects it. But basically, because we're removing the pi from that, it's rotating a lot less. If we multiply it by pi, it will rotate it from 90 degree, or from down, essentially, whatever, to completely vertical. So by multiplying it by pi, we're doing half a rotation, essentially. 2 pi would give us the whole rotation. So this is in radians. So in radians, an entire revolution is 2 pi. So in here, by multiplying it by pi and knowing that this is between negative 0.5 to 0.5, that's will be negative half of pi to half of pi, which will give us half a rotation. It's kind of confusing. Don't worry about it too much at the moment. We'll go back, revisit this soon, and have a closer look at it. But basically, that means the angle 1, which is responsible for this first part here, this first link, will rotate from negative 0.5 pi, which is facing down, to 0.5 pi, which is facing up. So it basically rotates that line around that way. So if we look, actually, let's just comment out that part. So we're just looking at the first segment. So it's going to rotate from facing down to facing up, depending on the x position of the thing. So angle will be negative half of pi to half of pi. And then in segment, we basically tell it, start drawing xy. So if we look up here, x is 50, y is 100. So that's basically the starting position, 50 this way and 100 down, and rotate it by angle. So if we look at how this works, we translate by x and y. So we're going to move our cursor out 50 out this way and then 100 down this way. We're going to rotate it by that angle A, so rotate it round. This is negative 0.5 pi, and this is 0.5 pi over here, so rotate that. And then we're just going to draw a line, which is 0 by, if we look at the definition, so line has 4 parameters, which is the x coordinate, the y coordinate, the x length, and the y length. So because we've called translate, we could actually have gotten rid of this and said like that, and that will sort of work. It'll work a little bit differently, but it's often easier to actually, when we're doing sort of 2D, 3D graphics, to actually translate the position and then draw the line. So essentially we've moved it out. We're going to say start drawing at 0 by 0, which is actually now set to 50 by 100, and draw this seg length long, which is 50. So draw a line 50 long from wherever we're starting from, that way. But because we rotate it first, it's going to rotate the whole thing. Does anyone have a piece of paper I could borrow? And actually, I'll do it on the whiteboard. I'll do it on these whiteboards here. Sorry, we won't be able to get this on the camera. Hopefully that wasn't important. If it was, they probably should have made a note of it. So, here is our screen, and we want to draw a line out in it. So what we could do is we could say, okay, start drawing a line at 50 by 100, and draw that 100 units long in the x dimension, and 0 units long in the y dimension, and that would be our line of code. So if we write line 50, 100, 100, 0, that will draw a line like that. 50 units out this way, 100 units out this way, and 100 units long. Everyone follow that? Make sense? Yep. The alternative way of doing that is, knowing that our origin or our start position is up in this corner, we could say, all right, let's translate this by 50 by 100. And what that's effectively going to do is it's going to move our origin position to here. So this is 100, this is 50. So anything we start drawing from is going to now start drawing from that point, rather than up here. So if I ran our same line of code before, this is actually going to add another 100 and another 50, and it's going to draw a line out there. But because we're already where we want to start drawing from, we can actually just say, okay, make that 0, make that 0, make that 100. And these two things do the same job as right. Does everyone sort of see how that works? So we can either say, in our line thing, we can say, start drawing from this position at this length, or we can say, actually move the cursor, move the origin to this point, and then just draw the line. So these two comments here are more or less the same here. There is a slight difference in that if we drew another one, or if we did another one now, like that, this would start drawing because the origin's up here. Our first line would be here, and our second line would be 10 this way by 100, so it'd be along like that. So it would again start drawing from the origin because we haven't updated the origin, whereas here if we did 10, 100, whatever, it would start drawing that from that origin. So you just always have to think about whereabouts the origin is when you start drawing. And you know, if you don't call translate, if you don't call rotate, if you don't call scale, it will always be sitting at the top left corner of the screen, and everything you draw will be relative to the top left corner of the screen. If you move it by using translate, rotate, or scale, it will be somewhere different, so you might need to reset it. So let's go back to this example here, and let's look at the second part. So angle 1 basically computes a value between negative 0.5 pi and 0.5 pi. So this one based on the x position. This thing does the same thing based on the y position. And if we look at the way, now I don't think this is necessarily the best written piece of code because it's a little bit confusing to look at, but so what we do now is we draw our first segment. Are you guys able to read this? Pen's not very bright, hopefully. Let me know if you can't read it anyway, and I'll see if I can do a little bit better. So, in our example, we call translate x, y. So we move along x, move down y, and then we rotate by r. So let's say we rotate it down here. So normally, you know, we're drawing, so x is in that direction, y is in that direction, but if we rotate that, we're effectively like rotating around that point. So we rotate round, and then when we draw our line, it'll go down like that. Right, so everyone follow that? And it's the same thing. So normally our origin starts off at 0, 0, with x going this way and y going this way. If we call rotate on this and we rotate it by r degrees that way, so it's like that. Anytime I try and move in the x dimension, I'm actually going to be moving diagonally down. Anytime I move in the y dimension, I'm going to be moving diagonally across. So it's just something to keep in mind that once you change the origin, it will remain changed until you reset it back or whatever else. But yeah, so let's have a look. So we've drawn this first line, and then what we do when we get to the second time is we call, now instead of calling x and y segment, we're calling seg length. So the seg length is the length of the line. So what that's effectively going to do is originally we started here and we drew this line, which is seg length long, and now we actually translate along seg length. So what we're going to do is we're actually going to move the cursor so that the cursor is now sitting here. We rotate this by angle 2. So if this is angle 1, we have another rotation, angle 2, which will rotate in some direction, and then we just draw our line out that way. So what happens? Well, essentially, every time we draw this, we draw the first thing, and it will pop out here, and that will swing round. But the second line will always start drawing from the end of that first line, and it will draw with its own rotation around that. Right? Everyone happy?
Would it be different if you switch the 2 segments?
Yep, so it would. So let's refresh our memory. So this is what the original one looks like. So you can see the second wiggly part here is attached to the first one. If we change the order, this is a good question. It's very different. So essentially what's happening now is instead of doing it like this, we draw the first, so we're drawing the second line first. And if you remember, the things were, so segment originally it's x, y, angle 1, and then it was segment seg length 0, angle 2. So if we do these the other way around, segment S1, 0, angle 2, segment x, y, angle 1, what happens is essentially we're going to run this operation first. So our cursor starts here. We're going to move out seg length, and then we're going to rotate by angle 2. And let's say we'll draw our line out here. So this is, let me see if I can get these to sort of add up. So let's say that this is, so this angle here is, actually no, I'm going to put that down, sorry, I'll change this a wee bit. So if we think about it, like this is moving this way to begin with, and then it goes this way. So this angle is actually effectively this in here. So originally, well, when we draw that on here, it'll look like that, right? So we've updated our cursor here, we've rotated it by angle 2, and then we draw that line. Then what we do is we call segment x, y, a1, but our cursor is no longer starting up here, it's starting up here. And now x goes in this direction, and y goes in this direction. So we're going to move x units out this way, and then y units out this way. So our cursor will sort of start around here, and then we're going to rotate that by angle 1, which originally rotated that way, so it's now probably going to point down here. And so we're going to end up with our second segment is pointing down here. Right? So sorry, there's no easy way to explain this sort of stuff, unfortunately.
Wouldn't the angle be the other way?
So we've basically, originally x and y went like that, and then we moved down here and we rotate it that way.
So you from horizontal to that way?
Yep, so we move.
What do you think for the second one then? Oh no, I mean like that one, the A2.
A2.
The angle is that one, but it shouldn't be the other way.
So in this example, x points, we change x so it's pointing this way, and then when we get to this one,
It's down, right?
yep.
So it's that angle, not that one.
Let me find one pen, two pens, actually.
But that's the path it uses, not the
Okay, so if we consider the black pen here to be the x-axis and the green pen to be the y-axis, what we do is we shift this down to here, and then we rotate it that way. So it's rotating clockwise, and then we come down here and we rotate clockwise again, and that's A. So here, or A2, sorry, so A2 is a clockwise rotation. So here we get a clockwise rotation, and then when we move this, we're going to be moving it so the x dimension now points this way, so we're going to move it some way this way, and then the y dimension points out here. And then we rotate. This one here was originally a clockwise rotation, so, and that's going to be a clockwise rotation. Yeah, unfortunately, I've yet to find a way to make this more intuitive to teach, because it really is just something you just have to keep working out until you get your head around. I mean, often there's still times when I get confused when I'm working with this sort of stuff. But the thing to remember is that, you know, these things are cumulative. So if I move and then rotate, move and then rotate. So this is a clockwise rotation. This is a clockwise rotation. So if we do the same thing, that's going to be a clockwise rotation. That's going to be a clockwise rotation.
Is it one of those anti-clockwise though? Because it's negative pi.
Yeah, it is in this example, but I was trying to make it slightly simpler. Yeah, so as Robert's pointed out, this is actually negative pi here, so it's actually reverse, but I was trying to sort of keep things simple to, to not complicate things. But you can see now, like if we look at this, the top one up here, that is this segment here. So this, this segment here, which was originally our second one. So it's always we're always gonna start at 0, and then we're gonna shift out seg length, and then we're just gonna rotate around that. And then based on that position and rotation, we update x and y, which will move us somewhere around here and then draw it. So what is actually happening is that second piece is now actually rotating around, or that bottom piece rather is actually rotating around the top piece. It's quite far away, but it's still rotating around this point here. So if you watch it when it goes, it'll spin around and it'll always stay the same distance from that top point. So yeah, play with this as much as you can. It is really the only way to get your head around it, is just to experiment with this sort of stuff. It doesn't necessarily have to be in code. Like there's lots of sort of 3D modeling software, game engines and stuff like that, which allow you to play with these sorts of things in an IDE without having to, or in a nice environment which don't require code. But yeah. So we'll go back to our original example. So this is the idea behind this, is it's trying to show like a cumulative effect. So we draw one of these, this first segment here, and everything we do to the first segment affects the second segment. So its position, its rotation, stuff like that. However, let's say we wanted to draw these two things and have them independent of each other. So if I use push matrix and pop matrix now, you'll see that the two things are independent of each other. And what push matrix does is, if we go back to this example here, we can call, so we start off at the origin and what we're doing, and origin with x that way and y that way, and we call push matrix, and that will save that position. So it says, okay, the origin should be at 0 by 0, and the rotation should be x is this way, y is this way. And then I can go off and do whatever I want, move the origin, rotate the origin, so on and so forth. And while that's happening, all this information will be changing. But then as soon as I call pop matrix, it's going to take all this information and use that to update the origin. So it's basically going to say, well, this is what I've stored, so let's move that back. And the reason it's called push and pop is because it uses what's known as a stack. Is everyone familiar with the concept of stacks in programming? No? Okay, so we'll just go over it quickly. So basically, the idea behind a stack, we'll do this with a really basic example, is it's named after like a stack of things, so a stack of papers, whatever else. So let's say I want to store a stack of integers. So we'll say my first value is 1. Actually, yeah, let's just do 1, 2, 3, 4. So if I call push 1, push 2, push 3, push 4, and our stack will push 1 on, and we'll push 2 on, we'll push 3 on, and then we'll push 4 on. And then if I call pop, we imagine this is sitting on the ground, the only way we could go back through it is from the top down. So if I call pop, I'll get 4, and then that's going to be removed from the top of the stack. If I call pop again, I'll get 3. If I call pop again, I'll get 2. And if I call pop again, I'll get 1. And the stack is empty. So the idea is whatever data you put in, you pull it back in the opposite direction. So this works exactly the same in this 3D world, except we're doing it with origins. So let's say we have our example again. So our example, we start off here and that way. Then we move down to here, and we're going this way, draw that line, and then we go to here, and we're pointing this way. So if I call push matrix, and then draw segment whatever x, y, blah blah blah, and then I call push matrix, and then I call segment seg length. So this is the first one. So we're basically calling push matrix, segment, and then we call push matrix again, and then segment, and then we'll start popping. What we do is effectively our stack would say, okay, push matrix. So we're going to push this state on here. So we're going to say this is what it is, and here is at 0, 1, 0. And then we update everything. So we update the origin, everything to here. We call push matrix. We say, okay, now it is facing that way, and it is at x, y, y. And then we call pop. Well, then, sorry, let's do one more. Let's do push here. So then we move down here, we rotate again, and we call this push. So now we can say this is facing that way, and it is x plus segment times angle 1 y. I can't even figure it out off the top of my head, but you know, basically what we've done is we've stored, you know, each of these different states as we go along. Then, if at any point in time we want to go back to a state, we can just keep on popping back up these over and over again. So, you know, what we could do is we could say we want to draw something which goes like that, and then draw something at the end, and like that. What we could keep doing is we could push, 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 pop, push, so on and so forth. So we just keep on going back down the line at each time and drawing, going down different paths. So, yeah, hopefully that makes some sense. Everyone sort of comfortable with that?
So why you don't push, like, let's say you didn't do the second push. So that means the two orientations from the two segments will be combined.
So calling push won't actually change anything, it just stores the value. So for example, if we do, let's do this one again. So I have now no pushes, no pops, and you know, it works like that. If I push here, push here, push here, whatever. Oops. Need to mention pops and stuff, otherwise it's going to fill up. Pop, pop. It still works exactly the same. So it's not actually, in this case, it's pushing it just saves it. It's just like saving it to a piece of memory, and if we never recall that piece of memory, it's not going to change anything. So if you...
How are you going to use that piece of memory?
You can call pop, and that will restore it. So it's like saving the state of the file, or saving the state of the coordinate system, and then pop reloads that state.
It works without it.
What's that?
But it works without it.
Well, if you don't save anything, it's never gonna. Imagine it's like you know, typing in a document in Word, and you type it out, you save it, and then you type out some more and save it, and then you type out some more and save it. Then you can go back and open any of those previous files. But if you never save it, you just can't. It just means you can't go back, basically. So you know, say I do some stuff, I open Notepad, and I go, okay, 1. Let's say that is 1, and then I go 2, and let's just 2, and 3, and so it's 3. Let me just check this. I think I just did something saved. Okay, so I've pushed it at state 1, and we have 1. I've pushed it at state 2, we have 2. I've pushed it at state 3, and I have 3. So I don't actually need to save any of that stuff, but I'll always, if I don't save them, I'm always stuck with whatever the last change was. So I don't have a history. I can't go back anymore. Everyone all happy? It's, yeah, I'm sorry, it's quite complicated and I can't, there's not really any good way to explain it. It's just something you sort of have to get a feel for, really. The more you play with it, the easier it will get. Anyway, now that we've spent a lot of time talking about just this one thing, let's sort of go back. So for 3D graphics, in processing, you've got two options. You can use P3D, which we've just looked at. You can use OpenGL. P3D is simple. It's integrated directly into processing, so it's native. It's lightweight 3D, so it doesn't provide all the functionality of OpenGL, but it's fairly straightforward. And you enable it by using SizeX, SizeY P3D. OpenGL, on the other hand, supports everything, but it's quite complicated to set up, so we're not going to look at it too much. All right, so let's have a look at a simple P3D scene. Some of these first. So here is a simple P3D scene. There's got a lot of stuff we haven't looked at yet, but it's got a few things we have. Right, so we can see here size, we know that, set up 640 by 360, so a weird shaped window, and we're using P3D, so we're going to set it up for 3D environment. We're going to set the background to black. So we haven't looked at lights or no stroke yet, but we'll have a chat about those in a minute. And then we have this, so we push matrix, we save the state of the thing, we translate it, so we move in the origin, we're going to rotate it in the y-axis, rotate it in the x-axis, and then we're going to draw a box, then we're going to pop matrix. So everything which happens between this push matrix and the pop matrix is going to be thrown away essentially as soon as we call pop matrix. So we save the state, do some stuff, and then load the old state. We haven't seen no fill or stroke either, but we'll come back to those. Then we push matrix, so we save the state, we're going to move some stuff again, we're going to draw a sphere, we're going to pop the matrix. So everything which has happened within these two things is undone. Well, all the transformations have been undone. So if we run this now, this is what we get. So we have a sphere, which is just lines, and we have a cube. So let's have a look at some of these functions we didn't know. So lights turns on lighting, basically. If I turn lights off and we run that again, you're going to see that there's no, like this box previously had one side was shaded, or both sides were shaded and stuff like that. It had what's like 3D lighting applied to it. If I turn lights off, it's just going to draw it all white or whatever the current color is. You don't notice it so much on the sphere because it's just wireframe, but the same thing will happen there. So that's what lights do. So turn that back on, and now you can see, you know, these two sides are darker, so this has more of an illusion that it's 3D. Then we have no stroke. So let's turn that off. And potentially, yeah, so we can notice a slight difference. You can see now on this cube, we can see the edges being drawn. So stroke and no stroke with 3D models basically says draw the edges or don't draw the edges. So if we say no stroke, so watch these little grey lines around the outside when I restart it, they disappear. So it's basically saying don't draw any outlines. Then down here we do some stuff. We translate, we rotate, and we draw a box. So this box is here. And then we pop matrix, so we're going to move the cursor out, move it some ways, draw a box, and then return the cursor to where we started, we'll return the origin. And then down here we have no fill and stroke. So these, with knowing what no stroke does, we can probably figure out what no fill and stroke is. So if I turn no fill off, now the sphere is filled, so it has a whole bunch of things drawn, and we can actually see the effects of the lighting a lot better now. And obviously, stroke is just going to turn on the outlines. So if I turn that stroke off, it's just going to be a sphere like that. And this is just like everything else, it just takes a color value. So if you give it one color, it will just draw that RGB with that color. So we can specify, actually draw red, whatever else. And then we push matrix, move out a certain space, and draw a sphere.
If you pick up the first pop, will the sphere move more to the right then?
So we need to move the pop because you need to have as many pops as you can pushes. But yeah, if we move this, it'll now be relative to the position of the box. So with the box, we've moved it and then we've rotated it. So while it used to be to the side, like if you think about here's the box and here's the sphere. We used to start with our origin here, so we shift down and across, down and across. Now what we've done is we've shifted down and across and rotate, and then we push it out this way. So it's actually, from our perspective, now sitting behind the box because the box is being rotated. If we don't rotate those boxes, or if we don't rotate the box rather, it will be still on the screen. So it'll be further off to the side, as you suggested. So, you know, we move the box here, and then we start from this origin, we then move across and draw the sphere. But because we rotated the box so it was pointing backwards, we're actually pushing it further into the screen. Right. So everyone happy with that example? What all the various bits and pieces of it do? You know, the transformations and rotations is just something which you have to keep on playing with until you can sort of get around it. Right, so obviously there are things in processing which are default things. So we have box, sphere, and sphere detail as 3D primitives. We don't really have a lot. 2D primitives, we have arc, ellipse, line, point, quad, rect, triangle. 3D primitives, we actually only have 3. So we can draw boxes, we can draw spheres. What if we want to draw other things? Well, we can actually define things using this begin shape idea. So I don't know how much you guys know about 3D modeling, but essentially every 3D model ever in a computer is basically defined by a set of points known as vertices. So if we wanted to say have a cube will have 8 vertices, one for each corner on the cube, and then we basically define how those vertices are joined together with lines and whatever else to make a box. So we have an example here. New again. And here you see we have a pyramid essentially. So we have something which has a square base and then it's got 4 triangular sides. And if we just ignore all this translate, stroke, no fill stuff, this is essentially what's happening here. So we have our begin shape and our end shape, and then we define a bunch of vertices. This has not been laid out in a very good way. So I cannot tell which is which. What we can do is we can actually just try and figure out how this pyramid is built. We can have a look at each. So nothing. So here we've drawn a bunch of lines, and I think we'll look at this. We do look at this a little bit more in detail later. But basically, we have a set of vertices. So we say, okay, let's draw a line from this point to this point. I'm not sure why it didn't. Maybe it was actually. So I'll show you what I just did by putting lines in there in a second. But so these first two things, -100, -100, -100, that defines the x, y, z position of the first point. So one of these 2 points here, actually, this might probably be a better way to sort of illustrate to begin with. So if I say begin shape points, it'll tell us we just want to draw a bunch of points. And you can't really see them, unfortunately, because they're so far away, but there's a point there, there's a point there, there's a point there, there's a point there, and there will be a point hanging at the bottom here somewhere. And essentially what we're doing with that thing is we're joining all of those points up to make our pyramid. So if I take that off and take that off, we join those 1, 2, 3, 4, 5 points, and we'll end up with our pyramid. So 1, 2, 3, 4, 5. And what all of these vertices do is basically define, okay, this point connects to this point, this point connects to this point. And you see we've got a lot more vertices than we do points. That's just because we need to say, okay, this is how these two connect. We can't just say, here's a point, 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 connect them all, because we have no idea what point connects to other points, and so on. So often we'll sort of say, okay, connect this one to this one, and now connect this one to this one, now connect this one to this one. So that will give us 1, 2, 3, 4, 5, 6 vertice calls, but we've actually only used 3 points. So this is not a great example of how these things work, but it hopefully gives you an idea that you can say begin shape and throw in a bunch of points and it will draw it. So there are some examples which illustrate these things slightly better. So, and these ones I've actually written out. So if we go to topics, geometry, RGB cube, run this one. So here we go. So this is a nice cube, which is drawn, and the way this cube works, if we look at that, the corner facing us at the moment, that's black, so that's RGB 000. This corner is, this corner here is completely red, so that's RGB 25500. This one is green, so this is RGB 0255. This is blue, so it's 00255, and then each one is just added together. So blue and green make cyan, green and red make yellow. So this is an additive color, not subtractive. So subtractive is what you use to when you're drawing with paint, and blue and yellow make green. In the additive model, it's the other way. You get green and red make yellow, and blue and red make purple. And then finally, if you make all of them 255, 255, 255, we end up with white. So let's have a look at this code. Somewhere down here, so there's a whole bunch of stuff in here which is responsible for moving the cube based on the thing. But we have begin shape quads, so we'll look at the different types of begin shapes. But quads are exactly what they sound like. It is a quadrilateral. It is something with 4 sides. So if I comment out all but one of these quads, you see we have one side of our box. So on this one we have over here. So the fill basically defines what color that should be. So let's have a look. 111, for example, is white, so that will be that top right corner. 101 is magenta, so that's that bottom right corner. 001 is blue, so that's the bottom left corner, and this one 011 is cyan, so that's the top right corner. And if you look at this, they all go from so we've got the positions -1. Where is that? -1, 1, 1, 1, 1, 1, 1, -1, 1, and -1. So if we look at that, all of these are at 1, and this is the Z value, so this is the depth away from us. But if we look at these ones, we have, if we draw this on a grid, and we say, this is X, this is Y, and this is -1, this is 1, -1, 1. So -1 in the X column by 1 in the Y is that point there. 1, 1, so 1, 1 is that point there. 1 by -1, so that's 1 in the X, -1 in the Y, and -1 by -1 is that point there. So that's how we get 4 edges, or the 4 vertices of our quadrilateral. And you'll typically find, in fact, depending on how smart this is. Hopefully this will be, yeah. So if you look at that, if I change the order of these, it's all screwed up. So basically what I've done is, two of us will print negative 1, negative 1, 1. So I swap these two. So if we go negative 1, 1, 1, 1, negative 1, negative 1, 1, negative 1, if we do that again, we've got negative 1 by 1, is that one, got that one there. 1 by 1 is, oh, sorry, negative 1 by 1. So the first point is that one there. Second point is 1 by 1 is that one there. Negative 1 by negative 1 is that one there. That one's 1 by 1. So when it's tried to draw this, it's gone like that. And that's why it's tried to loop up that last part, and that's why we've essentially got a chunk hanging off the side of it. So it does matter what order these things are in. You basically need to think, if I was trying to draw a line around all these things, let's run through this example again. So we start at negative 1 by 1, and we're going to draw a line to 1 by 1. And then we're going to draw a line to negative 1 by negative 1. We're going to draw a line to 1 by negative 1. You can see now that that's not going to look like a cube, whereas if we do the same thing here, we're going to go negative 1 here, and then we do that one. And, oh, sorry, we're going from this one to this one, and then it's 1 by negative 1, so we'll go up here, and then negative 1 by negative 1 will go across here, and then it'll fill in that last thing, because we're told it's quadrilateral, we're told it's got 4 sides, and it said, okay, we've got 3 of them, so we're just going to take this last one and this one and draw a line between the two of them. So it is important what order you get these things in. If you get in the wrong order, your model will not look correct. And then let's have a look at some of them. So if we comment or uncomment some of the other ones, we'll see here's another side of it. So in this case, the x value is always 1 and the y and z value change, so that will position it in a different space. In this one, in fact, so in this one we can see the z value never changes. In this one we can see the z value never changes. So we know those two must be perpendicular or parallel. Sorry. So those will be the opposite sides of the cube. So there we go. There's the two opposite sides of the cube, and then if we look, we can actually match them up and pair. So it doesn't actually matter what order we put the whole quadrilateral, and it's just the vertices within the quadrilateral. So in this one, x never changes. In this one, x never changes. So those must be the two parallel sides. So that will give us a cube which is 4 sides, and then the last two, the two y values never change. So it's always 1. It's always negative 1, which will give us the top and the bottom cube. Right, everyone follow? Yep. It is confusing. What I often do if I am trying to build a 3D model or whatever from scratch is I will actually say a cube is often sort of the easiest way to go, because I mean cubes are like everything is just a straight line. But you'd be surprised at how often I, doing stuff, or some of the projects I've worked on, I need to draw a cube in code. But I will do, okay, so there are, if you look, I'm not very great drawing. There's my cube, and then I will say, okay, let's say everything on this, or this plane here is x is equal to -1 here. Oh, sorry, it should be 1. Y is equal to -1. Everything here is y equals 1. Here, x is equal to -1. X is equal to 1, and then backwards, z is equal to -1. Z is equal to 1. And then it's just a matter of going through each of these things. So, okay, I want to draw this front face. So everything on this front face is z equals -1. So -1, -1, -1, -1. So half of it. And then I'm just going to go -1 by -1. Do that one, and we're around to this one. So 1 by -1. We'll do this one. So that's x is still 1 by 1. And then we'll get around to this one, which is -1 by 1. And that will give me that side there. And then you just do that for another 1, 2, 3, 4, 5 sides. And you got yourself a cube. And this is why most people don't program graphics in code. Instead, they put things in a 3D modeling program and then they just load 3D model code. And we will look at how you do that later on. Right. So let's just have another look at what's this one here, vertices. So this is another interesting example. So you can see here, this is another thing which has been done in code, and it's kind of like a funnel type shape. And actually, before we do that, I might just pop through. So we saw in this one here, for example, we have begin shape. Actually, let's have a look. If we look at the RGB cube, we have begin shape quads. So we know each, because it's quad, it means it's quadrilateral, it's going to be shaped with 4 sides. So it could be a square, it could be a rectangle, it could be a parallelogram, it could be a trapezium. It's going to have 4 sides regardless. So we know we can look at every group of 4 points and say that is going to be one side of our object. There are other ways of representing it though, like these. So we could say points, and I showed you guys that one with the pyramid. So points, every vertex will be treated on its own, and a single point will just be drawn on the screen. We can do lines where it will basically take every 2 points and it'll just draw a line between them. So the points, we need to look at them in pairs. We can have a line loop where it will just continue. So if we say, here's a point, here's a point, here's a point, here's a point, it will go, okay, grab that one, that one, that one, and go back to loop that one. So actually, if I do these, so I go line loop, so lines, if we have one here, one here, one here, one here, it will say, okay, there's a line, points, one here, one here, one here, it will just go, there's a point. Yeah, so that's the difference between points, lines, and line loops. So points will just draw every single point. Lines will grab every 2 points and draw a line. Line loops will grab as many points as they can, connect them all together. Then we move on to triangles. So let's see. So let's do 1, 2, 3. So we do triangles. What that's going to do is it's going to grab every set of 3 points and draw a triangle. So 1, 2, 3. 1, 2, 3. Then we have a triangle strip. And that's where it starts getting a little bit confusing. 1, 2, 3, 4, 5, 6. What a triangle strip will do is it will grab the first 3 and go, and then it will take the last 2 points. So if this is 1, 2, 3, it will take the last 2 points and grab another point and make a triangle out of that. So if we done these 1, 5, 6, we'll go 1, 2, 3. Okay, get rid of 1, and we'll do 2, 3, 4. So that's a triangle there. And then we'll go, okay, 3, 4, 5. That's a triangle there. And then 4, 5, 6. That's a triangle there. So that's what a triangle strip will look like. And we have a triangle fan. So if we do triangle fans do not use them for structures like this. But the idea behind a triangle fan is we always keep the first point, and then we just grab consecutive 2 points. So we go 1, 2, 3, then we go 1, 3, 4, then we go 1, 4, 5, then we go 1, 5, 6. So that looks really ugly. The reason you use triangle fans is when you have something like this, and this is actually the reason why I wanted to mention that before I show that on the demo. Say we want to draw a circle. What we can do is we can say, okay, here's a starting point here, and let's just draw some points around the outside. So this is point 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. So what we're going to do is we're going to go 1, 2, 3, we're going to go 1, 3, 4, 1, 4, 5, 1, 5, 6, 1, 6, 7, 1, 7, 8, 1, 8, 9, 1, 9, 10, 1, 10, 11, and we're probably put another point there as well. 1, 11, 12. So you can see now we've essentially drawn kind of like a circle out of triangles. So if you want to draw a strip, use a triangle strip. If you want to draw a fan or circle, whatever, use a triangle fan. Do not mistake the two of these. If we tried to draw this like a fan, we would end up just do a simple basic one. We end up going do 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 do. So we sort of end up drawing the outline. We have this one weird thing in the middle, and then sort of an outline of it. So, you know, if you get something which looks like this, and you're trying to draw a circle, make sure you're using a triangle fan. If you're trying to draw a whole straight line, then try to use a triangle strip. And then the last two we have is quads. So quads are what we just saw. So if we have 1, 2, 3, 4, 5, 6, 7, 8, we'll just go up and grab 4 points for a quad, grab 4 points for a quad, and then a quad strip. Sorry, there's some space here, but we go 1, 2, 3, 4, and then what we're going to do, 4, 8, we use our last 2 points and grab another 2. So we go 3, 4, 5, 6, and then we'll do 5, 6, 7, 8. So it works exactly the same as a triangle strip, but with quads. And there is no triangle fan because that doesn't make sense. Right. So these are the examples we saw here. Triangle strip, ABC, BCD, CDE, DEF will be a strip. A triangle fan without fan, we go ABC, ACD, ADE, AEF. Right. And we must be pretty close on finishing this. Okay. So let's just have a look at this last demo here. Okay, so we have 2 things here, and hopefully you guys will be able to look at this and say, okay, I actually have a feeling I know what's going on here. So we have a circle part at the top, and that is probably made from a triangle fan. Yep. So we've got a triangle fan here, and then this sort of round part at the end, or this cylinder part at the end. I'll give you a hint. It's actually made, I'm pretty sure it's made of quads, not triangles, so it's not going to be a triangle strip. It's going to be a quad strip. Yep. So if we go down here and I draw a cylinder, we have quad strip, like we just suspected. And if we comment out that piece of code, find that we are missing the sides of our thing. There is actually another triangle fan in the back there that we weren't able to see before because it was always behind it. Then if we look down here, we'll see a triangle fan. So if we comment that out, this. Then you can see it's missing the top cap, it's hollow. So those are the 2 parts. Now the math behind this is a little bit more complicated because we have to basically curve around the outside. They could have done it manually as well, but this is obviously, if you're doing this triangle strip or this quad strip, you need to define each of these points manually and end up with a lot of code. Here they just they basically just multiply it by cosine and sine to work their way around it. Yeah, and then there's also the bottom radius in the cone as well. So we could do some interesting things, like we could change that from quad stretch to quads, and yeah, it's going to grab 4 points, and so we're going to end up with like this sort of sparkly thing, where instead of it's just essentially done every sort of second one, and yeah, in this case it's left out all the middle chunks of it. Yeah, and I think that's probably a good place to stop. So we have a whole other lecture. We're actually falling behind a little bit, but that's okay because I think we've got an extra week of lectures at the end if need be, the way Mark's budgeted it out. But yeah, we've got an extra set of, so Mark's going to be back next week, and he's going to be basically going over his lectures on elastic paper prototyping. It may not take him the full 2 lectures, so I'm going to be with you on Thursday, but we'll see what happens. But we're going to be continuing with 3D graphics whenever I start back. So we'll start looking at transformations. So this is stuff we looked about: scaling, rotation, order transformations. This is what you sort of mentioned before, like depending on what order you do things, you get different results. Transformation stacks, this is what we're talking about pushing top matrix. Scene graphs, which sort of solve the whole problem for you, but it's important to know how they sort of work underlying, and stuff around 3D view volumes, illumination, materials, texturing, loading 3D models, and so on and so forth. So now that we've been through all that, you guys don't need to come. Yeah, so we'll have a look at that next time. Otherwise, yeah.